Hello everyone, and welcome to another recitation video. Today's topic is energy, work, and the first law of thermodynamics. Make sure to check out the lecture video on the same topic if you haven't already. I will put the link down in the description below and somewhere on this screen, probably on the top right. Now, without further ado, let's get into it. The first problem is a rather simple one. We have a river flowing with a flow rate of 500 meters cubed per second, and it's going towards a lake which is 90 meters below. The problem says if the river's velocity, average velocity, is 3 meters per second, what is the power generation potential of this river? Now first we need to find a location to put our turbine that will generate the highest power. Now take note that the turbine is a mechanical device. Mechanical devices convert the mechanical energy of a flowing fluid directly into power or work. Now the equation for mechanical energy of a fluid is actually the mass flow of the fluid times its mechanical energy per unit mass, which is kinetic energy plus potential energy plus pressure times the specific volume of the fluid. Okay, so let's say we have these three options to put our turbine. One up there, one in the middle here, and one down here on the lake surface. Now let's compare them. At point 1, we have kinetic energy, but because the turbine and the river are on the same line, we don't have any potential energy. At point 2, we still have the kinetic energy, and we also have a bit of potential energy for this distance, right? At point 3, we have the kinetic energy, we have potential energy, but this time the potential energy is this much. From this comparison, we can see that putting a turbine here actually generates the highest power possible. So the work of the turbine, or better say the power of the turbine, is actually equal to mechanical energy of the fluid. Mechanical energy is m dot times E, which is m dot times velocity squared over 2 plus GH plus P specific volume. Now in the case of our river, we know that the pressure upstream of the river, because it is in contact with atmospheric air, is 1 atmosphere pressure here, and on the surface of the lake after the turbine, the pressure is still 1 atmosphere. So the change of mechanical energy due to change of pressure is negligible. There is none. So this term goes away. These two terms remain. We need to clarify m dot as well before moving on. So we have a number here, volumetric flow rate, which we know is v dot. And then we have the average velocity of the fluid here. The density of the water is not given, but we all know that the density of water is 1,000 kilograms per meters cubed. Now with this information, we can readily find m dot. M dot is rho times volumetric flow rate, which is 1,000 times 500, which is 5 10 to 5 kilograms per second. Okay, we have m dot. Now let's continue with the rest of the terms in this equation. So power, potential, or max is 5 10 to 5 times. Now, what is the velocity? The velocity that we get at point 3 is 3 squared over 2 plus potential energy at point 3 is G times H. H is 90 meters. G, for simplicity, we are going to take as 10. So that is 10 times 90. This thing here is 9 over 2, which is 4.5. And this thing here is 900. So we are looking at 5 times 10 to 5 times 904.5. Okay, I just moved the equation up here so we can continue. Now, if we do a bit of calculations, we get W dot maximum is 4,520 times 10 to the power of 5. Now about the units, be very careful. The units for potential and kinetic energies, the way that we have written them, are joules per kilogram. So these guys are joules per kilogram, while the mass flow rate is kilograms per second. So multiplying these two, the number that you get is joules per second or watts. But it's more convenient to express the power with a unit that doesn't have this many zeros. So you can say, hey, W dot is 4.52 to the power of 8, or 4.52 times 10 to 5 kilowatts, or 452 megawatts. Please take note that this number is the maximum power that this river can theoretically provide. Now, the actual output of the turbine will definitely be lower than this number because of all the losses and friction and everything else. Another thing to pay attention to is that here in the mechanical energy equation, this represents the kinetic energy of the fluid, whereas this number represents the potential energy. As you can see, the potential energy is way larger than the kinetic energy. So sometimes in our calculations, it is all right to neglect the kinetic energy. Okay, problem 2. This is basically the same problem. We have a hydraulic turbine coupled with a generator, and it's producing electricity from water supply that is 120 meters below the surface of a lake. Okay, so if this is the lake, and we have some pipes taking the water down, we have a turbine here which is connected to a generator, right? And the generator is producing electricity, and the turbine is generating power or work for the generator. Okay, so again, the distance between the turbine and the free surface of the lake is 120 meters. The mass flow rate is directly given, 1500 kilograms per second. We now know that the power that the turbine produces is equal the mechanical energy of the fluid, which is m dot kinetic energy plus potential energy plus the pressure energy. We don't have any information about the velocity of the flow, but as we shown in previous problem, we can neglect the kinetic energy. We can also neglect the pressure because the flow again is not pressurized, and we are left with the potential energy only, which is G times H. Now W dot of the turbine will be 1500 times, again we take G as 10 for simplicity, 10 times 120, and if we do a bit of calculations, we get W dot of the turbine is 1.8 times 10 to 6 joules per second, which is watts. So W dot of the turbine is 1.8 times 10 to 6 watts, which is 1.8 times to 3 kilowatts, which is 1.8 megawatts. That's it. Okay, I'm going to show you how to convert watts to megawatts. Now we know that 1 megawatts is actually 1 million watts, right? So this is the conversion rate. Now, I'm going to say, hey, my power is 1.8 times 10 to the power of 6 watts. Then I'm going to multiply this number with a fraction of 1. This fraction has the unit that I want to end up with in the numerator and has the conversion rate in the denominator. So watts cancel each other, 10 to 6 cancels 10 to 6. We end up with 1.8 megawatts. That's how you do conversions. Okay, problem 3 is more of a conceptual problem. It says we are having a room which is completely insulated, and there are a few candles inside burning, and the temperature inside the room is rising. What are the energy interactions that are happening inside this system? Okay, so first of all, let's draw our system. So this is our insulated room. When you put hatched lines like this on one side or on one of the walls, it represents insulation. So if you see something like this in your problems, it means that the room, the box, whatever, the tank is insulated. We also have a candle inside, which is burning. Now let's do an energy analysis. Now, because of the insulation, no heat can enter or exit the room, right? Also, from what we have read in the problem, no work interactions are happening. But the problem states that the temperature is rising. So what's happening here? Now, if you take a look at this from the first law perspective, we can say Q net of our system minus W net of our system is equal to the change of total energy of our system. Now, based on our analysis, both Q and W are 0. And what we get is that the change of energy of our system is actually 0. So what does that mean? The energy of a system is the summation of kinetic energy plus potential energy plus the internal energy. Now, our room and the candle inside of it does not have any motion, and it doesn't have any change of elevation. So both kinetic energy and potential energies are out of the picture. So delta E is actually delta U. internal energy only. So combining these two equations, equation 1 and equation 2, we get that delta U, or delta internal energy of the system, is 0, which means internal energy at the final state with the higher temperature is equal to internal energy of the initial state. So what does this mean? It means that some of the chemical energy of the system, which is stored inside the candle, is being released through the process of burning. Now, chemical energy is a form of hidden energy, hidden internal energy, right? Whereas temperature is a representation of sensible heat or sensible energy. So what is happening is our system is turning chemical energy into sensible energy. So at initial state, we have higher levels of chemical energy, and at the final state, we have higher level of sensible energy. But the point that you need to pay attention to is that the total energy of our system, which includes the room and the candles, have not changed. It has only converted from chemical energy into sensible energy or molecular activity. Sensible energy is a representation of molecular activity. Okay, problem 4. We have two cranes, crane A and crane B, that are lifting the same box 20 meters up. Crane A does this job in 20 seconds, while crane B does it in 10 seconds. Now, the question asks whether or not the work that both cranes do are different. It also asks whether the powers are different. So let's get to it. Work of crane A is the force times the distance that the force is acting on the object. Now we have the box here. The force in question is the weight of the box, which is m times gravitational acceleration. And we are moving this box 20 meters up. So the work involved is mg, force, times the distance, 20. Right? So how about crane B? It's the same equation. Has the force changed? No. The force is still mg. Has the distance changed? No, it's still 20 meters. So again, the work of crane B is mg times 20. So you can clearly see that the work of crane A is equal to crane B. Power, on the other hand, is a different story. Power is work over the time that it takes to perform the work. So the power of crane A is work A over delta TA, which is mg20 over 20 seconds. Gives you mg. Power of crane B is work of crane B over delta T of crane B, which is mg20 over 10 seconds this time, which is 2 mg. So we can conclude that the power of crane B is twice the power of crane A. Okay, we have an escalator that is moving 50 people, average 75 kilograms each, with a speed of 0.6 meters per second, up a slope of 45 degrees. It is asking for the minimum power input to run this escalator. Now, let's first draw a schematic of the problem. Like always, if you don't get a schematic, draw one yourself. So this is the slope, and people are on this escalator. I'm going to just assume that all of them are inside this box. So this is 50 people times 75 kilograms. So that is the mass of this box. And it's moving with a velocity of 0.6 meters per second up the slope. It asks for the minimum power input. Okay, let's take a look. What are the energy interactions involved in this problem? We know that the Q net, or rather Q dot net, because we are dealing with power here, minus W dot net is ddt of the energy of a system, right? What is the energy of a system? The energy of a system is its kinetic energy plus its potential energy plus its internal energy, right? So from what we can gather from the problem, there is no heat transfer involved. We also know that W net or W dot net is actually W dot out, the work that the system does, minus W dot in, the power that it consumes. Escalator is actually consuming power from the electric grid, right? It is consuming electrical power. So we know W dot in is the minimum power input that we need. Is the escalator producing any work? The answer is no. It is not generating any work. So that term is out. Now, if we plug in the W net that we found here into our first law equation, we get that W dot in is equal to ddt of kinetic energy, which is mass times velocity squared over 2, plus potential energy, which is mgh, the distance, the elevation of this box of mass from the ground, plus internal energy. Now in this particular problem, the internal energy of the system is not changing because we are not seeing any temperature changes, we don't see any phase change, any chemical reaction, any nuclear reaction. So it is safe to say that there is no change of internal energy. Kinetic energy as well, because these people are always at any time are moving with a velocity of 0.6 meters per second. So the velocity doesn't change. Velocity is always constant. So ddt of the kinetic energy will be 0 because of the constant velocity. So what we get is that W dot in is actually ddt of the mgh. Mass doesn't change, g doesn't change, so they are the constants, they jump out. H, however, changes because the box is here at this time. A second later, the box is here, and h is different. So h is a function of time, h dot. So this is the equation that we are looking for. Now we have a new unknown, h dot. So what is h dot? In order to find h dot, we need to take a closer look at the triangle that we have. If x represents the location of the box and h represents the elevation of the box with respect to here, then h over x is the sine of 45 degrees, right? Because of the trigonometric equation, the definition of sines. So h is actually x times sine 45, right? Now we can make a derivation with respect to time. I can say h dot is actually x dot times sine 45. So what is x dot? X dot is the rate at which this box moves along the x-axis. From the problem, we know that the box is moving with velocity 0.6 meters per second on the x-axis. So x dot is actually 0.6 meters per second. Plug in, and you get that h dot is 0.6 meters per second times sine 44. Okay, we can now plug in everything. W dot in is equal to mass is 50 times 75 times g, which we take it as 10, times h dot, which is 0.6 square root of 2 over 2. Doing a bit of calculations, we get that the work input is 15.75 kilowatts. Okay, let's move on to problem 6. It says we are heating water in a closed pot over some sort of heater. 30 kilojoules of heat is given directly into the pot, and 5 kilojoules of it is wasted. We have a paddle wheel which is also steering the water inside, and the work of it is estimated to be 500 joules. What is the final energy of the system if the initial energy was 10 kilojoules? Okay, so this is a rather easy question. This is our system, the H2O. We are introducing heat here, 30 kilojoules. The system is losing heat for 5 kilojoules. We also have a paddle wheel steering for 500 joules. And the question asks for the final total energy. So first law states that Q net minus W net is delta E of the system. Q net is Q in minus Q out. W net is work out minus work in. Q in is 30 kilojoules. Q out is 5 kilojoules. Work out, there is no work going out, is 0. Work coming in is 500 joules, which is 0.5 kilojoules. So plugging in everything that we have, we get 25 plus 0.5 is E2 minus E1, which is E2 minus E1 is given to as 10 kilojoules. So doing a bit of algebra and calculation, we get E2 is actually 35.5 kilojoules. Okay, so this is very similar to the problem that we had at the beginning of the video, where we had a turbine in the way of a river. But this time we have efficiencies involved. So this problem actually is discussing efficiency. So we have a lake. And again, we have a piping system. And then we have a turbine. This turbine is connected to a generator, which is producing electricity, right? Okay, the mass flow rate inside the pipe is given 1500 kilograms per second. And The difference of elevation is also known. It is 70 meters below. And one thing that we need to pay attention to is that the problem explicitly says that the power output of the turbine is 800 kilowatts. And the power generated, the electric power generated by the generator is 750 kilowatts. Now, these numbers are important. Now, from before, we know how to find the potential or the maximum work that the turbine can produce. The maximum work input of the turbine is the mechanical energy of the fluid, which is m dot kinetic energy, potential energy. Now, this is negligible, this also is negligible, and we end up with this, which is 1500 times GH. It is 1500 times 10 times 70. We get that the input energy of the turbine, the mechanical energy of the fluid, that is the input energy of our turbine, is 1,050,000 watts, which can be converted to kilowatts. It is 1,050 kilowatts, right? Now, in order to answer part A, the turbine efficiency, we need to know the power output over power input, right? So the power output is the number that the problem says, 800. Power input is what we found here, the mechanical energy of the fluid that was delivered to the turbine. It's 1050. Doing the math, we get that the efficiency of the turbine is 0.76, or the turbine efficiency is 76%. Okay, I just cleared the calculations and moved our results from part A up here. Now, in order to answer part B, we know that the overall efficiency of a combined system is the product of the efficiency of its individual components. So it will be the efficiency of the turbine times the efficiency of the generator, right? We already have the efficiency of the turbine. We need to find the efficiency of the generator. So the efficiency of the generator is, again, the electric power output over the mechanical power input, right? So the generator is getting 800 kilowatts of mechanical energy, mechanical power through the turbine here, and it's producing 750 kilowatts of electric power. Doing the math, we get that the efficiency of the generator is 0.9375, or 93.75%. Now, the overall efficiency is going to be the efficiency of the turbine times the efficiency of the generator, which is 0.76 times 0.9375. Doing the math, we get that the overall efficiency is 0.7125. Overall eta, or overall efficiency, is 71.25%. Problem 8. We have a pump that is taking water from the lake surface and dumps it in a water tank 20 meters above the ground. If the pump is dumping water with a volumetric flow rate of 70 liters per second, and if the label on the pump says that it consumes 18 kilowatts of electricity, what is the efficiency of the pump and what is the pressure rise of water? A pump is the polar opposite of a turbine. The turbine converts the mechanical energy of a flowing fluid into power, while the pump converts the power, like electric power or anything, into mechanical energy and delivers it into the flowing fluid. This is our pump here, giving power to the fluid, to the flow. So the power of the pump is actually equal to the mechanical energy change between the lake surface and the tank, right? So that will be m dot times kinetic energy plus potential energy plus p nu. Now between the lake surface and the tank, the kinetic energy and p nu are negligible, as we discussed before. So we end up with W dot of a pump is actually m dot times GH. Now let's find m dot. So the problem says that we have a volumetric flow rate of 70 liters per second. We need to convert that into mass flow rate. 1 liter is 10 to minus 3 meters cubed. So our volumetric flow rate is actually 70 times 10 to minus 3 meters cubed per second. Now I know that my mass flow rate is density times the volumetric flow rate. Density of water is always 1,000 kilograms per meters cubed. So it's 1,000 times 70 times 10 to minus 3, which is 70 kilograms per second. So we found the mass flow rate. We take G as 10 for simplicity, and we take H as 20 meters because the problem states. We end up with power of the pump is 70 times 10 times 20, which is 14,000 watts or 14 kilowatts. Now the label on our pump says it consumes 18 kilowatts of power from the electric grid. Efficiency is the power output or power going out over power input, right? So it's 14 kilowatts over 18 kilowatts, which is 0.77. So the efficiency of the pump is actually 77%. Okay, I just moved the power of the pump, the output power of the pump, up here, and we want to answer part B. Now the part B asks for the pressure rise inside the pump. We are going to take a control volume around our pump, and let's focus on that control volume. So we have the pump, we have flow coming in, we have flow going out, right? If I write down the first law of thermodynamics, I'll get Q dot net minus W dot net plus, so we have mass flow rates coming in and out, plus all the mass inflow energy minus all the mass flow outgoing energy is equal to ddt of the total energy of the system. Now, for our problem here, the pump does not have any heat interactions, no heat transfer involved. So this is going to be 0. W dot net, we know that W dot net is W dot out minus W dot in. The system is not generating any work, so this is 0. And W dot in is actually the W dot of the pump. So we get that W dot of the pump plus M dot E in minus E out, which is the total energy of the fluid coming in minus the total energy of the fluid going out, is ddt, the energy of the system. Now let's expand that. W dot of the pump plus M dot E in minus E out is equal to ddt of kinetic energy of the control volume plus the potential energy of the control volume plus the internal energy of the control volume. Now for the control volume that we have here, there is no change in kinetic energy because the control volume is not moving. There is no change of potential energy because the elevation of the control volume is not changing. And there is no change of internal energy because the temperature is not changing. There is no phase change happening, no chemical reaction happening, no nothing. So ddt of all these three energies are going to be 0. So we end up with this equation. W dot of the pump is equal to M dot energy out minus energy in. Okay, so I just moved our equation up here and cleared the calculation space. Now, what are the energy in and energy going out? Now, energy coming in or energy going out is actually the sum of, this is for the fluid, for the flowing fluid. So the energy is the kinetic energy of the fluid plus the potential energy of the fluid plus the pressure of the flow times the specific volume, right? So with this knowledge, we can say that the W dot of the pump is M dot times kinetic energy of the fluid going out minus the kinetic energy of the fluid coming in plus potential energy of the fluid going out minus the potential energy of the fluid coming in plus P specific volume of the fluid going out minus P. Between entrance and exit, the kinetic energy or the change of kinetic energy is negligible. The reason that we are neglecting this is, first, from the previous problems, we saw that the kinetic energy in these problems are actually rather small in comparison with other forms of energy. But in this problem particularly, the problem doesn't say anything about the velocities at the exit and entrance of the pump. So it is a good bet to assume that this is negligible. Also, the potential energy, the difference of potential energy between the inlet and the outlet of the pump is this elevation, like the size or the height of the pump, which in comparison to 20 meters that the water is rising is a negligible number. So this is going to be neglected as well. Now remember that the specific volume of water is actually the inverse of the density, and the density of water does not change. So I can rewrite this equation as pump power is mass flow rate times P outlet minus P inlet, or P exit minus P inlet, over density. Now, P outlet minus P inlet is the delta P, or the pressure rise that we are looking for. So delta P is actually density times power of the pump over mass flow rate. Plugging in numbers, we get that delta P is 1000 times 14 over 70, which is 200 kilopascals. Okay, so here we are at our final problem. This is the most challenging one yet. We have a motor that is powering up a pump, which is pumping oil at a rate of 0.1 meters cubed per second. And the pressure rise through the pump is 400 kilopascals. And we are looking for the efficiency of the pump. Okay, so let's get to it. First of all, we need to find the power of the pump. In order to do that, we are going to do the same thing that we did in the last problem. We are going to take a control volume and write the first law of thermodynamics. So this is the control volume that we are taking. So let's take a closer look. We have the pump here. We have the discharge. And then we have the inlet or the suction of the pump here. Okay, the diameter of the outlet and the inlet sections of the pump are different. A few things to clear before moving forward. We need to find the density of the oil. It is given in a specific gravity. So Sg of the oil is given at 0.86. Now remember that the specific gravity is the density of oil over the density of water, which is the density of oil over 1,000 kilograms per meters cube is equal to 0.86. It says density of the oil is 860 kilograms per meters cube. Now, let's see what the volumetric flow rate is giving us. Now, this is a general tip. So far, in the problems before, we were neglecting the kinetic energy of the fluid because we didn't have enough information, and we also knew that the kinetic energy is negligible compared to potential and pressure energies. But here, the reason that the diameter sizes are given is for us to find the velocity of the fluid and include the kinetic energy. So if you want to get the full credit on a problem like this, you need to find the velocities at the entrance and exit of this pump. So let's get to that. Let's call the entrance section 1, and let's call the exit section 2. Now, at the entrance, volumetric flow rate is velocity average times the cross-section area of the pipe, right? So volumetric flow rate is given. It is 0.1 meters cubed per second. At entrance, volumetric flow rate is velocity 1 times area, which is pi d1 squared over 4. Plug in numbers, you get 0.1 is velocity 1 times pi times d1, which is 8 centimeters, which is 0.08 meters squared over 4. From here, doing some calculations, we get that the velocity is 19.9 meters per second. Okay, we can do the same thing at the exit. So at section 2, or at the exit, we know that the volumetric flow rate is equal to velocity 2 times the area, which is pi d2 squared over 4, which if we plug in numbers is 0.1 equal to velocity 2 times pi 12 centimeters, which is 0.12 meters squared over 4. Now plug in numbers and we get that the velocity at the exit is 8.84 meters per second. Okay, so we have the velocities at the entrance and the exit of this control volume. Let's write them down here. So 19.9 meters per second at the entrance and 8.89 meters per second at the exit. Okay, so I just moved everything that we know up here to clear the calculation space. Now we can continue with our problem. So just like the last problem, the first law is written here, q dot net minus w dot net plus m dot energy coming in minus m dot energy going out is equal to the rate of change of the energy of our control volume, right? So there are no heat transfers involved, so this is going to be 0. W net is, just like last problem, is going to be minus power of the pump, and the rest we can expand here. So this is equal to d dt of the energy of the control volume, which is the kinetic energy of the control volume, potential energy of the control volume, plus the internal energy of the control volume. Again, kinetic energy of the control volume is not changing because it's not moving. The potential energy is 0 because we don't have any changes in elevation, and also no phase change, no temperature rises, no nothing. So the internal energy is also 0. So this entire thing is 0. Now we can reorganize the equation into this. Power of the pump is mass flow times energy going out, or energy at section 2, minus energy coming in at section 1, E1. Now mass flow rate, we already know it is density times volumetric flow rate. We have both. The mechanical energy of a moving fluid is its kinetic energy plus its potential energy plus the pressure over density. Now, for a problem like this, the potential energy difference between the exit and the inlet is negligible. So we can drop this term, and we are left with the kinetic and the pressure terms. So let's continue with that. So W dot of the pump is m dot, which is 860 times 0.1 times mechanical energy at the exit is velocity 2 squared over 2 plus P2 over rho minus velocity 1 squared over 2 minus P1 over rho. So let's plug in some numbers. W dot of the pump is 86 times 889 squared over 2 minus the velocity at section 1, which is 19.9 squared over 2, plus the pressures are unknown. So we can bundle them up here and say P2 minus P1 over 860, which is the density of the oil. P2 and P1 are not known individually, but we know their difference. P2 minus P1 is the pressure rise that the problem has given us. It's 400. So this is 400 kilopascals. Now, be careful. We need to convert kilopascals to pascals here in order to have unit consistency. So this is actually 400 times 10 to the power of 3 pascals. So let's do some calculations. The power of the pump is 26,369.95 watts, or around 26.37 kilowatts. So as you can see, we had to go through a lot of calculations to actually get our final answer. But the problem is not over yet. we still need to find the pump efficiency. So I just moved up the power of the pump, the one that we calculated up here, and cleared the calculation area so we can continue with the problem. We are going to find the efficiency of the pump. So the motor that is powering up the pump is getting 35 kilowatts of power from the electric grid, and it's delivering some power to the pump. We need to first calculate that in order to be able to find the pump efficiency. So the efficiency of the motor, it's the power output of the motor, so the power output, over the electric power it consumes, right? We know that the efficiency is 80%, so 0.8 is equal to the output power of the motor over 35 kilowatts of electric power. So doing the calculations, we get that the power output of the motor is 28 kilowatts. So 28 kilowatts of power is delivered to the pump. How much does the pump deliver to the oil? That is 26.37. Using these two numbers, we can find the efficiency of the pump. So the efficiency of the pump is equal to the power output of the pump over the power output of the motor. That is 26.37 over 28. Now, if we do the calculations, we get that the efficiency is 0.94, or the efficiency of the pump is 94%. Now, in order to clarify what we did here, we took the efficiency of the motor and calculated how much power exits the motor and enters the pump. So 28 kilowatts of power entered the pump. Out of this 28 kilowatts of power, 26.37 kilowatts was delivered to oil. So the efficiency of the pump is the power it delivered to the oil over the power it got from the motor. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like, as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again, and see you in another video.